Welcome to Lecture 35, whose subject is the origin of magnetism. Now, what could be more obvious than the origin of magnetism? It's magnets. Here's my big bar magnet. It's got a north pole. It's got a south pole. The north poles repel. It's hard to put them together. The opposite poles attract. We know about magnetism, and magnets as the source of magnetism. But I want to probe more deeply into the question, what is the origin of magnetism? And the first thing I want to ask is, what would happen if I could isolate the north pole of this magnet and the south pole of this magnet? Or could I do that? Are there, in magnetism, the analogs of positive and negative electric charge? Positive being like a north pole, negative being like a south pole. I want to explore that question. And I'm going to do it with a slightly less massive magnet, which I have here. And I'm going to demonstrate that this magnet is a magnet. It affects that compass needle. And right now I am pulling the south pole of the compass needle toward the magnet. If I turn the magnet around, I pull the north pole toward the magnet. And so this magnet clearly has two distinct poles, a north pole and a south pole. And what I want to do is try to isolate the north and south poles of this magnet so I can have just pure north pole and pure south pole. So let's step over to our workshop. I will clamp my magnet, and now I'm going to whack it with this hammer. That's why I used a smaller magnet for this experiment. Now I have two halves of the magnet. Is this the north half and this the south half? Let's go see. Well, that end attracts the south pole of the compass. Turn it around, and if this is an isolated pole, the other end ought to attract the south pole as well. But no, it attracts the north pole. So this little piece still has two poles, a north pole and a south pole. How about the other half? Well, that half attracts the south pole. That half attracts the north pole. This piece has two poles also. We can't split the magnet into a separate north and south pole. And I could keep whacking that magnet into smaller and smaller and smaller and smaller pieces, and each piece would be a complete magnet with both a north and a south pole. That's a fundamental fact about magnetism as we understand it. There is no such thing as an isolated magnetic pole. At least we don't think there is. An isolated magnetic pole would be called a magnetic monopole. They would be isolated south and north magnetic poles that would behave just as a single north pole, no southness to it at all, and vice versa. They would be the magnetic analogs of electric charge. They've never been found, although scientists have searched for them. There are theories of the early universe that suggest these magnetic monopoles might exist. But we have never found any, and if they do exist, there are good reasons from astrophysical arguments to suggest that they are very rare. So as far as we're concerned, there are no magnetic monopoles. And that immediately leads to a fundamental law of magnetism, which harps back to Gauss's law that I introduced for electricity. Remember Gauss's law? It said if we draw a closed surface around some charge distribution, the total number of field lines emerging from that closed surface depended on nothing but the enclosed charge. Well, there is no magnetic charge, at least none that we've ever discovered, and that means any closed surface we draw will have zero magnetic field lines emerging from it. So that tells something about how the magnetic field is supposed to behave. Another way of putting that is magnetic field lines don't begin or end, because when we had electric field lines, they began or ended only on charge. So there are no magnetic monopoles. So then we have to ask the question, if there aren't sort of isolated magnetic north and south poles that would be the analogs of electric charge in giving rise to magnetism, what is the source of magnetism? Well, let me remind you again, say it big and loud and clear, what magnetism is all about. Magnetism is fundamentally about moving electric charge. And I said it in the previous lecture, moving electric charge responds to magnetic fields, and we saw how that happens and how we use it to make electric motors and cyclotrons and all kinds of things. Now we have the flip side of that. Moving charge also causes magnetic fields. Magnetism is about moving electric charge. Moving electric charge is both what responds to magnetism and is the source of magnetism. So let me give you some examples of that. First, let's look at how the magnetic field arises from an electric current. So here I have a piece of wire carrying a current I, and current, of course, is moving electric charge. I have some point P off to the right where I want to evaluate the magnetic field. And the rule for finding the magnetic field in this case is somewhat like, but more complicated than Coulomb's law for the field associated with an electric charge. It's called the Biot-Savart law, and it says a very short length of current produces a magnetic field that falls off as 1 over r squared, just like the field of a point charge does the electric field of a point charge. The field direction is perpendicular to both the current and a line extending from the current to the point where I'm trying to evaluate the field. So that gets kind of complicated, but it means out at my point P here, the magnetic field is pointing into the screen. So the field, as you've already seen with magnetism, there's this complicated three-dimensionality to it. But basically, this is the magnetic analog of Coulomb's law. Now, here's a difference. You can't have just a single tiny isolated piece of current. If you did, charge wouldn't be conserved. What you have are complete circuits carrying charge around in a complete circuit. So even though the magnetic field of a tiny little infinitesimal hunk of that current falls off as 1 over r squared, when you add up vectorially the magnetic fields of all the pieces of that current, you will never get a magnetic field that falls off as 1 over r squared. If you had a magnetic field that fell off as 1 over r squared, it would be the field of a magnetic monopole, just like the electric field that falls off like 1 over r squared is the field of an electric point charge. So the magnetic field of a current is given by this Biot-Savart law, and what ends up happening is that the magnetic field lines ultimately wrap around the currents which are their sources. They form closed loops. Remember, magnetic field lines can't begin or end. So even though electric current, moving electric charge, is the source of magnetic field, the field lines don't begin on that source. Instead, they wrap around that source. And let me do one example. I'm not going to actually go through the calculation, but I'm going to tell you what the result is for the magnetic field of a long, straight wire. And here's a picture of what the magnetic field of a long, straight wire looks like. It consists of nice concentric circles wrapping around the wire, and it turns out that the magnetic field of a long, straight wire falls off with distance as the inverse of the distance from the wire. And I'm not going to prove that. It takes a little bit of calculus to do it. But it's not a surprising result either, because this field is falling off in only 2 dimensions instead of 3, so it falls off more slowly than an inverse square field from a point-like object. Incidentally, the electric field of a long, straight, charged wire also falls off inversely with distance, although that field points radially outward from the wire, which is its source. But the magnetic field falls off inversely with distance, and it wraps around the conductor. And by the way, you'll notice in this expression for B, the magnetic field of the long, straight wire, several things. The current I is upstairs in that expression, and that makes sense because the stronger the current, the stronger the magnetic field. If the current were 0, there'd be no magnetic field. Downstairs, we got some constants, 2 pi, and we got the radial distance from the thin wire. There's something else in there. There's a constant. It's given by the Greek mu, the Greek letter mu, lowercase mu, with a sub-zero. It's called mu naught or mu sub-zero. And it is essentially a magnetic analog of that Coulomb constant K that we dealt with. 2 electromagnetic constants, the Coulomb constant and the magnetic constant mu naught. And these are going to play a very big role as we come to the end of electromagnetism. So keep them both in mind. And this one has to do with simple things like magnetic fields caused by currents flowing in wires. The Coulomb constant had to do with simple things like measuring the force between those charged balloons that I showed you earlier. That magnetic constant happens to have the value 4 pi times 10 to the minus 7 Tesla meters per ampere. That happens to be an exactly defined value. By the way, the value of the Coulomb constant K is also exactly defined, but you won't see why that is until we get to the end of electromagnetism. So there's the magnetic field of a long, straight wire. And let's pause and look at what that actually looks like. Let's do a demonstration of it. So by a long, straight wire, actually, I mean a wire that's infinitely long, but if I'm close to any long wire, close compared to its length, it's going to behave essentially like an infinitely long wire, and it's going to produce this magnetic field that consists of concentric circles that wrap around it. So here I have a straight wire. It would be nicer if it went all the way through the table, but it ends here. So it isn't a perfectly long wire, but I have at the bottom of it some compasses, which are all pointing in more or less the same directions. In a laboratory situation, it's always hard to get compasses to point right because there's always metal around, the ferrous metal that's affecting them. I'm going to turn on this power supply, which is going to put a hefty 10 amperes of current through that vertical wire, and watch what happens to the compass needles as I turn it on. You can see them swinging in direction. And you can kind of imagine, although it isn't terribly obvious, that the magnetic field is wrapping around that wire. Now, I can't really get them close enough, and I can't really get the wire all the way through the table, but I'll use my little probe that we had last time, and I will move this probe around. And remember, the probe is essentially pointing in the direction of the magnetic field. And you can see as I wrap the probe around, it kind of traces out a direction which is sort of circular around the wire. It's not perfect because this wire isn't infinitely long, and there are other things around. Even those magnets are probably influencing things a little bit. But there is the sense that there is clearly a magnetic field around this wire. And it is, in some sense, wrapping around the wire. It isn't forming perfect circles, but it's doing a pretty good job of it. So there's the magnetic field of a long, straight wire. By the way, it was the Dane Hans Christian Ørsted who discovered this relationship between electric current and the production of magnetic field back in 1820. So this is something we've known about for quite a while. So there is the magnetic field of a current-carrying wire. Now the compasses have relaxed back to their normal position, which is to point in the direction of the Earth's relatively weak magnetic field, and they're pointing northward. So that is the magnetic field of a long, straight wire. Now, let's look at some interesting things that happen if we have long, straight wires carrying current. Because currents respond to magnetic fields, as we saw in the preceding lecture, and because currents give rise to magnetic fields, if I have two wires in each other's vicinity, they will actually give rise to magnetic forces on each other. And so let's take a look at what that looks like. So here are a couple of parallel wires carrying current. I happen to show them carrying current in the same direction. We'll draw the magnetic field of wire number 1, and that consists of circular field lines that wrap around the wire, and right at where wire 2 is, there is some of wire 1's magnetic field. Remember the whole field concept. Something responds to the field in its immediate vicinity. So if I apply the right-hand rule, and if I look at that Biot-Savart law, you can figure out which direction things wrap around the current. You take your finger and you point it in the direction of the current, and the magnetic field wraps around in the direction of your fingers, of your right hand. By the way, if you're left-handed, don't feel left out. I'm left-handed. We could have defined everything the opposite way, but this is just a convention. It would have all worked if we defined it the other way. Anyway, right-hand rule, wrap around, and so the magnetic field of wire 1 is pointing upward at the location of wire 2. Now, wire 2 has a current to the right. It has a magnetic field pointing upward. If you do the right-hand rule, the other right-hand rule, and you take the direction of that current to the right, and you ask what has to happen for it to curl onto the direction of B, which is upward, you get a force toward wire 1. So wire 2 feels a magnetic force toward wire 1. And not surprisingly, wire 1 feels a force toward wire 2. Those two wires are attracted. By the way, the forces have the same magnitude because the currents, I'm assuming, in the two wires, well, they don't have to be the same, but it's the product of those two currents. One current gives rise to the magnetic field, the other current gives rise to the response, and either way, the term includes the product of those two currents. There it is, force is proportional to I1, I2, and it's going to be inversely proportional, not surprising, to the distance between them because we've seen that the magnetic force of a long straight wire falls off inversely with the distance from the wire. And so these two wires carrying currents in the same direction are attracted. That may sound counterintuitive because you think, oh, opposites attract and likes repel. Here's a case where likes, two currents in the same direction, attract. If I reversed one of those currents, clearly the direction of the force would reverse and the two wires would repel. So wires in opposite directions repel. A couple of examples of this. One is when you hear electrical equipment humming, you hear a big transformer saying, what you're actually hearing is the vibration of the wires under the response of this force. You'll have many, many turns of wire in a typical electrical device. So you've got parallel wires carrying current in the same direction, but the current is alternating. because it's alternating current, and so the force changes with time and the wires move back and forth a little bit, and that's the origin of the hum you hear. The definition of the ampere, and from it the definition of the coulomb, the formal definition is actually in terms of the force between wires of a certain length when they're a certain distance apart, and if the force is a certain number of newtons, then that defines a current of 1 ampere. So there's the force between electric currents in current-carrying wires. If the currents are in the same direction, the force is attractive. If the currents are in opposite direction, the force is repulsive. Let's look at some other configurations. Here's another important configuration, a loop of current, such as I looked at in the previous lecture with this copper rectangular loop, but maybe even easier to visualize this circular copper loop. Let's ask what would happen if current were flowing in this. Well, if I look really closely, so close that I don't even notice the thing is curved, I'm going to see magnetic field lines surrounding that wire pretty much the same way I would see them surrounding a big, long, infinitely long straight wire. But if I begin to look farther away, I'm going to see field lines that loop around the wires something like this, and they become distorted from exact circles. And I'm not going to prove it, but this field, when you get far enough out, begins to fall off as the inverse cube of the distance. And that should ring a bell. We found that the field of an electric dipole consisting of 2 electric point charges fell off like the inverse cube of the distance. And if you did the challenge, you actually worked that out for yourself. So there's the field falling off as the inverse cube of the distance. And if you look at this field and see what it looks a lot like the field of an electric dipole. It's not an electric dipole field. This is not a pair of point charges. It's a circular current loop. And in fact, if we were really far from any current loop, no matter what its shape, it also looks like a dipole. Makes a field that looks like a dipole. An example is Earth's magnetic field. Down in the Earth's liquid core, the Earth has a solid inner core because the pressure is so high, but the outer core is liquid, and there are currents flowing in that core. They're generated by the motions of the Earth's rotation and convective motions associated with heating, and they cause currents, and the currents give rise to a magnetic field, and it is approximately, in the relatively near vicinity of Earth, a dipole field. So that's the origin of the Earth's magnetic field, and it falls off approximately again as 1 over r cubed. So Earth's magnetic field originates from current loops, not a single loop of wire, but currents flowing in this liquid core. Let's do some comparisons between electricity and magnetism, because I think you can begin to see now we're kind of converging on what was first a study of electricity and next a study of magnetism, and now we're converging on what's really one unified branch of physics, electromagnetism. So let's look, for example, at these dipoles that we've studied. At the top we have the magnetic dipole that I just talked about. It could be created from a current flowing in a small loop. Its field falls off as 1 over r cubed, and as I showed when we talked about how to make an electric motor, I showed it with the rectangular loop, but it's true for any loop, it experiences a torque when you put it in a magnetic field. The electric dipole is a very different beast in its origin. It's created by 2 point charges. We don't have 2 isolated magnetic, quote, point charges. We don't have magnetic monopoles, isolated north and south magnetic poles. We make magnetic dipoles with current loops, but we make electric dipoles with isolated positive and negative point charges. And you can see here the dipole field configurations, at least far from the structure, are quite similar. In fact, they're exactly similar if you get far enough out. The electric dipole falls off as 1 over r cubed, and the electric field of the dipole falls as 1 over r cubed, and it too experiences a torque in an electric field. So there are the 2 dipoles, analogous but not the same. Let's look a little more deeply at questions of electricity versus magnetism. The simplest electrical entity is the point charge. That's the simplest thing you can have electrically and have some interesting electricity happening. It has a radially outward field, spherically symmetric, pointing radially outward in all directions, and falls off as 1 over r squared. You can make a dipole in electricity, but that's more complicated. You take 2 point charges, put them together to make a dipole. The simplest magnetic entity, in contrast, is the current loop. We can't have, at least in steady state, and we'll talk more about that later on, you can't have a current that isn't forming a complete loop. So the simplest thing you can make magnetically is a current loop, and a current loop is basically a dipole, and it makes a dipole field that falls off as 1 over r cubed. Well, before we go on, let's just look at some comparisons of some simple field configurations for electricity and magnetism. So on the left, I have electricity. And an electric dipole consists of 2-point charges, and it makes this characteristic dipole field with these lobe-like field lines. On the right, we have the magnetic dipole formed by a current loop. At the perspective of these drawings, the current loop and the 2-point charges are so small you don't see them, and the fields look identical. That field falls off as 1 over r cubed, as we've seen for the electric dipole and as I've showed you for the magnetic dipole. The second row shows a point charge, the 1 over r squared field, associated with a point charge, or in fact any spherically symmetric distribution of electric charge. There is no such thing as a magnetic monopole, no magnetic point charge, and there's no way to put together a completely spherically symmetric distribution of steady current either. You could make current flowing steadily radially outward, but you couldn't have that be steady. You couldn't put together a spherically symmetric distribution of current. There are no magnetic monopoles, and there are no magnetic fields that fall off as 1 over r squared. And finally, a line of charge, as I indicated earlier, produces an electric field that points radially outward from the line, and because the fields are going out in only 2 dimensions instead of the 3 of a point charge, the field falls off only as 1 over r, and the same thing is true for a long straight wire. Its field falls off as 1 over r, but the field has a very different configuration. It has a configuration of these closed loops because magnetic field lines never begin or end, and those magnetic field lines are wrapping around the wire, whose current is the source of that magnetic field. So now we're beginning to get to the point where we understand these sort of analogs between electricity and magnetism. They're not the same thing, but they're intimately related, and ultimately they all depend on electric charge. In the electric case, fields are generated directly by electric charges. In the magnetic case, they're caused by and moving charges respond to magnetic fields. Well, at last, let's get to what you know about magnetism. Let's talk about magnets themselves. What makes a magnet? Well, if you believe everything I've said, in fact, if you believe the 2 things I said in this lecture and the previous one, and I said big and loud, you believe that the fundamentals of magnetism involve moving electric charge. So where does magnetism come from? Where does the magnetism of my big bar magnet come from? Where's the moving charge in this? Where are the currents in this? I haven't hooked this up to a battery to make some kind of magnetic current, make some kind of current and magnetism, but there are currents flowing in here and there are moving charges. Where are they? Well, they're atomic. And if you look at a very simple model for an atom, here's a utterly simple, naive model. And I have to say, this is a little bit too naive. I mean, quantum mechanics really governs how you would make a model of an atom. But if we think of an atom this way, as a positive charge with an electron circling around it, I've shown the electron with its velocity going that way. It's going clockwise when viewed from above. Because the electron is negative, the current associated with that electron is flowing in the other direction. And so if I use the right-hand rule and curl my right hands in the direction of that current, I find that that little tiny atomic current loop creates a magnetic dipole whose dipole vector, remember that dipole moment vector is perpendicular to the loop direction. And here's a little miniature version of that same big rectangular loop that I worked with in the preceding lecture. So there is a magnetic dipole moment associated with that thing. It would cause this atomic current loop to feel a torque in the presence of a magnetic field, for example. There's something else going on in atoms which is actually more important for the origin of magnetism, and that is electrons and other subatomic particles have a property called spin. And very, very crudely, you can think of it as a little ball that's spinning. Quantum mechanics tells us that's really not a very good picture at all, but let's think about it that way for a moment. And because the electron has charge and is spinning around, it too constitutes a miniature current loop-like structure, and consequently it also has a magnetic dipole moment, which could point in the same way as the one associated with the orbital motion of the electron, or it could point in the opposite direction. Here I've shown it pointing in the opposite direction. But the fact is, atoms become basically current loops. And that makes all matter have some magnetic properties. It's not just iron and steel. They're the most dramatically magnetic, but all matter has magnetic properties, and let's look at that. There are really 3 types of magnetism. There's what's called ferromagnetism, and that's the magnetism we're familiar with. So, when I grab this magnet and hear that clunk as these 2 magnets come together, or when I picked up that wrench with this magnet. That's ferromagnetism. When you stick a magnet on your refrigerator, you're dealing with ferromagnetism, and that magnetism is obvious and strong. And the magnetism you think of, that you're familiar with from everyday life, is ferromagnetism. What causes ferromagnetism? Well, remember that these atomic dipoles, these atomic current loops, would like to align themselves in magnetic fields. And the atomic currents are right next to other atoms in a typical material, and so you can imagine them influencing each other. You can also imagine them not influencing each other very strongly because they're pretty tiny little magnets, these things, these atoms. However, in ferromagnetic materials, there is a very strong interaction among nearby atomic magnetic dipoles, and it causes them all to align in the same direction. And these materials develop large, relatively large, still microscopic, but relatively large, many atoms, so-called domains, in which all the atomic dipoles are pointing in the same direction. And then in another domain, they might be pointing in a different direction. So a random piece of ferromagnetic material, of which iron and iron-containing compounds are most common, is not magnetized itself, but it's got all these magnetic domains. But you can magnetize it. You can force all those domains to line up by, for example, putting it in a strong magnetic field or banging it while it's pointing north. Various other things you can do to it to make it into a permanent magnet. And so if you line all those magnetic domains up, you have a permanent magnet. And a permanent magnet will attract any ferromagnetic material because it will result in those dipoles in the ferromagnetic material at least temporarily aligning, and then it too becomes a magnet, and its south pole gets formed, attracted to the north pole of the magnet you're starting with. And you get the common everyday phenomena of magnetism. So there's a very strong attraction of ferromagnetic material to magnets. There's another form of magnetism called paramagnetism, which is a lot less common. In paramagnetism, the individual atomic dipoles don't tend to align very strongly. And so paramagnetism is like ferromagnetism, but much, much, much weaker. It's a weak interaction among the dipoles, and so there is a very weak attraction to ferromagnets. One of the most strongly paramagnetic materials, incidentally, is something unusual, liquid oxygen. You can actually pour liquid oxygen between the poles of a magnet, and you'll see it attracted to those magnet poles because of that weak paramagnetic attraction. So we can measure paramagnetism, but it's not something you're going to see in everyday life. And finally, there's something called diamagnetism. We'll understand the origin of diamagnetism a little bit more when we've looked at another phenomenon, so-called electromagnetic induction. But diamagnetism is something that occurs when a magnetic field changes near these atomic dipoles, and they actually respond by developing a magnetic dipole moment that causes them to be repelled from magnets. So diamagnetism is the opposite of paramagnetism in a sense. It's a weak interaction, but it's a repulsive interaction. Diamagnetic materials are repelled from magnets. These magnetic moments have to be induced by changing magnetic fields as, for example, a magnet approaches a diamagnetic material. So there are really three types of magnetism, and almost all materials are magnetic to some extent. But the only one we see in everyday life is ferromagnetism. Now, all of them, though, involve moving electric charge. Let me end with this picture, which is an anatomy of a magnet. I'm looking at the magnet down from above on the left, and I'm looking at lots of little individual atomic currents. And within the magnet, they tend to cancel. But outside the magnet, if you add them up, it's as if a current were flowing perpetually around the outside of the magnet. And if you look at the picture on the right, you see that the resulting magnetic field is like the field of a lot of little loops of current. It's been stretched out over the length of the magnet, and it gives rise to this characteristic bar magnet field, which is a little bit like a stretched out dipole field. Get far enough away from it, it looks like the field of a pure dipole. That's where magnets really come from. Magnetism, again, is about moving electric charge, and the origin of magnets is the atomic current loops associated with orbital and electron spin motion in atoms. Well, let's summarize. Again, can't say it enough. Magnetism involves moving electric charge. That's the origin of magnetism, and that's what responds to magnetism. There are no magnetic monopoles. If there were, if we ever discover them, I'd have to say yes, and magnetic monopoles are also a source. But so far, we have not discovered any. That means magnetic field lines never begin or end. They encircle the currents that are their sources. And the simplest magnetic configuration, because we don't have magnetic point charges, is the dipole configuration. Current loops in particular produce dipole-like magnetic fields, and these atomic current loops align very strongly in ferromagnetic materials, and that's what makes ferromagnetism so strongly magnetic, and that's what allows us to make permanent magnets with the permanent alignment of these individual atomic current loops.